Hey, what's up guys, my name is Cherno and welcome to the 5th episode of the Sparky engine series in which we make a game engine from scratch in C++ and OpenGL. So, last time we talked about vector mathematics and particularly vec2, vec3s and vec4s. And we basically just implemented a class such as this one which has some basic vector operations and was capable of storing a number of floats. Okay, fantastic. So now what we want to do to continue on this little mini series of maths, we want to move on to matrices, particularly a 4x4 matrix. So matrices are used by OpenGL for pretty much everything to do with positioning elements, whether that be a projection matrix, which decides how we actually rasterize our objects onto the screen, and as in like what positions and what everything we use to actually position them finally, or whether it be transformation matrices, which we use to either move the camera or move objects and all of that good stuff, and get them wherever we want them to be. So matrices are very important because they let us manipulate our objects into their correct positions on screen. That is basically, at the end of the day, it comes down to that, right? It's just taking a bunch of data we have, such as a bunch of vertices, and putting them into and translating them into the right position on our screen in terms of pixels. Okay, that is what we use matrices for. So, one of the cool things matrices are for. So, this is episode 5, and what I want to do every 5 episodes, okay, is I want to have a little, I guess, review of what we're doing. Okay, specifically where we're going to go from here. So I want to basically plan out the next 5 episodes, and this will happen every 5 episodes. So what we're going to do today, obviously, is matrices. After that, I think we'll probably move on to, so once we have our basic maths classes that we need to actually, I guess, use with OpenGL, I want to move on to actual OpenGL code. So we haven't really written any OpenGL code as of right now. We've had some immediate mode and we've tested out some OpenGL 3 things to make sure glue was working perfectly, but we don't have we haven't written actual OpenGL code for the engine at all. Everything that we wrote was essentially just part of a test class, right? So what we want to do after this is probably move on to OpenGL stuff, right? So basically what I mean by that is we want to abstract OpenGL into classes that we can actually use in our engine, such as shaders, okay? Probably some kind of buffers so that we can actually store data in OpenGL and then tell it what to do with it, right? We want to also have a like a texture class, right? So that we can load and manage textures, including multiple textures, and of course we want to make a renderer. So I think what's going to happen is we're going to make this buffers class. It's not really a class, as in I probably will not be actually creating like a class literally called vertex buffer or buffer or something. This is more of an idea that we need to implement. But we will be having a class for actual shaders. Right, we'll be having a class for actual shaders, we'll be having a class for actual textures, and then we'll be having a an actual renderer class. So I think the order that I'll do these in, right? So this is going to be, this is episode 5, clearly. Shaders, I think, is what we'll do next. So that'll be episode 6, and that'll include loading from files as well as actually, I guess, loading the shaders into OpenGL and using them and all that good stuff. Textures will probably delay that as much as possible because that will actually involve us using a third-party library to decode the particular image format we want to import textures in, so whether that be JPEG or PNG, for example. So I don't really want to get into that just yet, but I'm just thinking maybe I should do the renderer first, or maybe I should do the textures first. So the shader episode will have probably a bit of actual stuff. Yeah, I guess. Okay, what we'll do is we'll make the renderer next. And the reason we'll do that is because I want to show you a more simple renderer before we actually move on to including textures in the whole process, because that will complicate things by a little bit. So I don't really want to do that too much, because I feel that you guys will understand like a more simple renderer, which just doesn't do textures. If we do that first, so we'll just have like solid colors and stuff. So once we do that and the renderer is good, this actually might be 2 episodes, I'm not sure, because I do want to explain that quite well. And then we'll move on to textures, which could be episode 8 or 9, okay? And after that, we'll be in a pretty good position. So I actually don't know what's going to happen after that. I doubt we'll be able to achieve all this in I doubt we'll be able to achieve all this in like 4 episodes. So I'm probably not going to plan any more ahead of that. But we'll do that. I don't know. If worst comes to worst, I mean, if best comes to best and we finish all this, we'll probably move on to doing something like a camera class so that we can actually have proper control of our view matrices, essentially. Okay, cool. So that's the plan. So let's talk about Mat 4 because that's what we're going to be doing today. So a matrix, or particularly this matrix 4, it's going to be a 4x4 matrix of floats. That's the data that's going to be behind it. Okay, and I keep pressing this button. I've got this button right here. Okay, it's mega annoying because I press it all the time, and it's basically like it basically right clicks. So I should probably just disable it from doing that. That would be nice. Anyway, we've got 4x4. We've got 16 floats. Okay, so essentially a matrix. If we take a look at this, essentially a matrix it's literally just an array of 16 floats. Okay. And then what we do with these floats, or what data we set in these floats, is going to be important because we're eventually going to parcel this data into OpenGL, okay? What OpenGL will do with that data is send it into our shaders, okay? And once it is in our shaders, we will use it for a lot of things, okay? It could be lighting calculations, but it will mostly probably be positioning, okay? Particularly positioning our vertices in the right location on the screen so that the rasterizer knows which pixels it has to, I guess, set, right? So that our object gets displayed on the screen. So that's kind of the general workflow, I guess, of having matrices in the first kind of place. Okay, so now that we've covered all that, let's talk about what this class will include. So a quick overview of this class will be as follows. So we're going to have a float array. We'll call the array something like elements, right? And then this will be 16, of course, because we have 16 elements. We need to have several constructors. We'll probably just have one constructor that is just simply a default constructor. We don't even have to do that really, but we will have it. It'll basically just set everything to 0. We'll have a constructor that takes in a diagonal value, and it will set the main diagonal in the matrix. So if we have a matrix and it's 4x4, so it has okay, let me put it this way, right? Everything that has a 1 in it is going to be part of the main diagonal, right? So this is the main diagonal. So we're going to set everything in the main diagonal to D. So for example, if we were to construct a matrix by calling this constructor like this, it would construct an identity matrix, right? We'll probably also have an identity method. We'll probably also have, we will definitely also have a multiplication, a multiply method, which will be pretty simple, I think. We'll also overload both the multiplication and the times equals operator to link into this multiply method. We'll also have, okay, so now that we've done this is basically all of the utility kind of methods that we need and the basic stuff that we really need to set all this stuff up. But right now, we can move on to our actual matrices. So how we're going to construct different matrices. So we're gonna have 2 projection matrices. We're going to have orthographic and perspective. Okay, so we need methods to construct those particular matrices. We also want our transformation matrices. Okay, so they will be essentially translation. I'm clicking that button again. Translation, rotation, and scale. Okay, and that is probably about it. I think that's about it. Let me just double check. Yep, that's really all we'll probably need. Okay, cool. So we also want to yeah, that's honestly about it. That's our matrix class. Okay, so let's get started. So back in here, under maths, obviously I'm going to add a new item. I'm going to call it mat4. It's going to be a header file. Okay, I'm going to pragma once that, so that we don't have multiple includes of this. And then I'll put it into our maths namespace, which we can find in any other maths class. So I'm just going to copy it from there, which is Sparky maths. Okay, so class mat4, again, I'll have a lowercase there so it matches GLSL. And we'll have... Okay, so the other thing is, it's not going to be a class, it's going to be a struct, the same way that we did with our vectors, right? It's going to be a struct, because I want everything to be public by default, which is a struct. Other than that, there's really no other reason to make it a struct over a class. It does the same thing. Okay, cool. So our elements are going to be, there's going to be 16 of them. Clearly, I'll probably just write it as 4x4, just to make more sense when you're reading the code, I guess. We'll make that default constructor. And we'll make one that takes in that main diagonal. What else do we have? I think we just had the... Yeah, it's okay. So we'll have a static method for the identity. So static mat4 identity, which will construct and return a brand new identity matrix. And okay, I guess we'll implement all of the prototypes now. So identity, and then we'll have multiply. So let's see. I'll probably just have this normal, I guess. So we'll probably return, okay, we'll return a reference to that, and we'll call it multiply, and then we'll take in a const mat4 other. So we'll talk a bit about matrix multiplication as well, because it's a bit different than standard multiplication. And then we have all of our actual like projection matrices and whatnot. So they'll all be static, so that we can basically, the way that I want to be able to call this, right, is going to be basically by just typing in mat4 identity, for example. And that will give me an identity matrix. So I can be like, yeah, that's my matrix. Or I can be like, I want an orthographic matrix. Or I want a projection, a perspective matrix, right? Or I want a translation, and you guys kind of get the picture, right? That's how I want to be able to do this, and it'll just return a new one. So we'll have a static mat4 orthographic. So an orthographic matrix is a type of projection matrix where essentially things that are further away, so things that have a, I guess, a greater z value or a smaller z value, depending on how you set it up, will not actually be physically smaller. They won't get scaled down. They'll actually stay the same size. But other than that, it's just a standard way to present pixels onto our screen, basically. So the way that an orthographic matrix is typically constructed is by setting 6 clipping planes. Okay, so in 3 dimensions. So we have left and right, right? So we set the horizontal, the horizontal clipping planes. So to explain this a little bit, or a lot a bit, we have, this is annoying, it's like that. Okay, we have a screen, right? This is our window, this is our game window, right? What we need to do is we need to tell OpenGL how much fits into that window, essentially. So we need to be like, anything past a certain point, so if we have something like a rectangle that we render, yeah, anything that's past a certain point, so it's like a left side boundary, anything that's past this boundary will not be rendered. Okay, so only this is what will actually be rendered. So if I kind of use more meaningful colors maybe, this is kind of the idea. So this stuff that's in red will just get clipped. It won't actually get, it won't get drawn, right? Because it's off the screen. So we need to define these boundaries, and there has to be 6 of them. So there's these 4, obviously. So we've got our left, our right, our like top, which will actually be here, and our bottom. Well, when I say top is downstairs, I really mean, I don't know why I wrote it that way, but this is usually the negative, and this is usually the positive. Whereas if you talk about a normal kind of windowing system, usually 0, 0 is up here rather than down there. But OpenGL usually, again, you can make 0, 0 up here. That's totally all right. If you just make, for example, if this was your window height and you wanted it to be like this, you could make the, like the top, for example, be 0, and then the bottom be like your height, right? Or you could, of course, do it the other way and make height, and make this thing height, and then this thing 0, which would mean that if you draw something at 0, 0, it will draw it in the bottom left rather than the top left. So you can set this up however you like, but really you're just defining these planes, right? And then you also have to set a near plane and a far plane, right? So that pretend this is like your matrix, right? You have to set up this near plane and that far plane as well, so that objects that are too close to the camera or too close to, based on their Z position basically, will also not get drawn, and things that are too far away will also not get drawn. Okay, so you're setting up these clipping planes. Whereas a perspective matrix, objects that are further away actually do become smaller. They get scaled down. So and it's more of like a frustum that looks like this, where you kind of start off with nothing, and then you kind of branch out. And then how much you see here, right? This angle that gets created like that is your field of view, essentially. So you don't specify a clipping plane, right? You do for the near and the far. So you specify a near, let's just say here, and then this would be like your eye or something, right? You specify a near to clip and a far plane to clip so that nothing gets drawn too far or whatever. But then all you do is you specify a field of view and then an aspect ratio. So if we're on a 16:9 window, we'll probably just put 16 and 9 or something like that, right? Or 16 divided by 9 will be the aspect ratio, right? So that's the idea. And then all you specify is a field of view, okay? So it's a bit different than clipping planes, which is traditionally what you would do in an orthographic projection. Okay, now that stuff has been said, we can move on to actually implementing it. So, float left, float right, float. I'm thinking what will it be? I guess we'll just go float top, float bottom, float near, float far. Okay, so those are basically just the clipping planes, left, right, top, bottom, near, far. That's it. You just specify floats for them, and that is it. And then for you know what? Actually, we'll go bottom first. It doesn't actually matter. It's just that I'm just thinking about how I write it, because obviously these are just parameter names, and we'll deal with them appropriately in the actual implementation, but I'm thinking this might be a better way to do it. Just how we call it, basically. Okay, and finally, or not finally, but I guess finally for our projection matrices, for this, all we need to specify is a float field of view, right? We need to specify an aspect ratio, okay? And then we just need to specify near and a far. All right, and that's it. Those are our projection matrices done. Okay, cool. So, next up are some pretty sweet translation matrices. So, to do that, we'll have a static. Okay, one thing I'll quickly do as well is I'll include, we'll include maths.h, all right, so that we get all the relevant classes from that. And then I'll make a static mat for, so we'll start with translation, right? So the translation is pretty simple. All we need for that really is a vec3. So we'll take in a const vec3 reference called translation, I guess. And that's all we need for that. You guys will see in the implementation how we actually do that. Now rotation's a bit different. So we specify the angle, and then we essentially specify the axis. So that'll be a const vec3 axis. All right. It doesn't have to be a reference. We'll keep it as that though. Okay, so there we go. And then finally, we have a scale matrix. So a scale matrix is going to work the same way. We basically just specify scale. So it's the same way as translation is what I really meant. We just specify scale and that's it. Okay, cool. So that is basically all of the actual matrix constructors that we have, right? Now what we want to do is point out the actual operations we have between matrices. So for example, multiplication, that's really the only one we're going to have. So to multiply matrices, you could make this static as well. I'm probably not going to. So we'll have a mat for, we've already done that multiply, but what I mean is actual operators. So we'll have a mat for, okay, so if we go back to vec2, for example, and we take a look at how we made the multiplication operator here, you can see we marked it as a friend. So we'll do the exact same thing with this, right? we're just multiplying two matrices together. So we'll have a mat4, it'll be an operator, it'll take in a left and a const right. Okay, that's all it's doing. And then the equals, or the times equals operator, which is what we see here, will do exactly the same thing that it does here. All right. So we kind of have that whole thing. So I think I might actually just pull this up here so that they're kind of grouped, right? And we'll just make a bit more sense. And then we'll just do this. Okay, cool. So there you go. That is our basic outline for the matrix class. So let's start with implementing all this stuff. Let's go right click, add new item. We'll make a mat4.cpp file, right? We'll include our mat4, and we will obviously include the namespace and whatnot. We can probably close our vectors now. Okay, cool. So let's begin. So mat4, so the default thing. So essentially our plan is simple. We just want to go through every element, which we know is going to be 4 times 4 or 16, and we want to set, we don't even need that, we want to set it equal to, so let's see, what are the elements, right? Elements I equal to 0. So you can do a for loop, you can do something like memset instead, and then just set everything to 0 because it's 0, so all the bytes will be 0. Up to you. I'm probably just going to write it like this. This probably makes the most sense to when you're actually reading the code. Okay, it'll just instantiate everything to 0. Diagonal is going to be kind of the same thing, except obviously not in the sense that it's going to basically do this, but set 0 plus, okay, so 0 plus 0 times 4, it will set to 1, okay? And then if you do it this way, there's the concern of, oh, but am I not setting things twice, right? I'm setting all this to 0, and then I'm setting everything else, and then I'm changing 0. So for example, I'm setting elements at index 0 to 0, and then I'm setting elements at index 0 to 1. My goodness. Why this is so terribly inefficient. I don't know about debug mode, but in release mode, this will definitely be optimized out. So it'll be like, you know what, and we'll check this out later, okay? Remind me, stream. But that's the idea. So yes, and of course we want to be setting to diagonal, not 1. But yeah, so the idea is all this stuff should get optimized out, and it should literally just convert this into essentially setting everything to 0 except for these two, which we'll set to that. Okay, cool. So there we go. This will work, and this obviously makes the most sense when you read it. Cool. So identity. Let's move on to that. So this returns a mat4. It's called identity, and it will be an example. It'll just be basically the same, and it will be the same as just mat4 1.0f. Okay, that's it. So now that we've made that, we can move on to the more fun things like multiply. So let's move on to that, and I'll explain how that works. So we want to take in another matrix, which will be multiplying the current matrix by, and we'll be returning a reference, because this is not a static method. All it is going to do is just multiply our current matrix with whatever we specify here and return our current matrix, or this. Okay, that's all it's doing. So let's talk about matrix multiplication. So basically, if we're multiplying two matrices together, okay, what will actually happen is, suppose A is, I'm just going to do this in a 2x2 matrix, but suppose A has something like 1, 2, 3, 4, and we're multiplying it with 5, 6, 7, 8. Okay, I probably should have written them as 1, 2, 3, 4 if we want to be strictly in column major. I should have talked about that. I'll talk about which major ordering and whatnot we'll be using in a minute. But if we do something like this, this will not simply equal 5, 12, 21, and 32. Yeah, that will not be the answer. What it will actually do is it'll take the row of this, right, and multiply it with the column of this, in the sense that what we do is we go 1 times 5 plus 2 times 7, and then that will be the first index. So this is what this equals. That's not correct, right? It'll be that. And then we'll multiply the second and so on and so forth. So this is how it works. It's a bit different than what you might be accustomed to. And then this will of course give us that first element. So back in code, to make that work that way, to make this work, what I want to do is implement some kind of, so again, what we need to do is we need to take the column, let's quickly talk about column major ordering as well. So one thing that's really important is how we decide to order our matrices. Since we have this float of elements, and all it is this one huge linear list of data with indices, and this goes all the way up to 15, right? We need to actually decide how it gets constructed into what appears to be a two-dimensional set of data, right? Whether or not 0, 1, 2, 3 appear like this, and then we have 4, 5, 6 all the way up to 15, or the other thing we have, and we could do, is have it appear like this, right? All the way up to 15, okay? So whether we choose to basically go down the column or across the row, the way we're going to do it is down the column, like this, okay? Not like this. The reason we're going to do it like this, and the only reason we're going to do it like this, is because that is the format that OpenGL operates in, okay? This is called column major ordering. Yeah? Whereas this is called row major ordering. What that means is that if we're in column major ordering, the way that we address the index of this array, if it was a linear, just a normal single-dimensional array of floats, which is what it is we can say this is our elements array, right? We can call it by basically saying what row we want plus what column we want times the width, which is 4. Okay, that is how we address it. So it looks a bit it looks a bit weird because essentially row kind of comes first, and you're like, what do you mean? Because obviously if I want like let's just say I want element X here, which happens to be at, it happens to be 2 down and 1 across, right? What I do is I put that 2 down first, I put that 1 across, and then I multiply it by 4, and that will actually give me 0, 1, 2, 3, 4, 5, 6. It should give me 6. Lol, that's not 6. What did I screw up? I screwed up the fact that this is not correct. Wait. What? Column 1. What? Have I out-mathed myself? Oh, it is 6. I'm an idiot. Sorry, it's quite late. Obviously this will get calculated first. So 2 plus 1 times 4 is 6. Okay? So there we go. There's our index. That's how we calculate the index. Whereas over here we'd have the column first plus the row times the width. Okay? And that's it. So that being said, that's how we're going to structure all this, and this is kind of the indexing that we will use. It's really important that you get this indexing right, because if you use the wrong indexing format, such as row major, and you give it to OpenGL and you don't tell OpenGL to transpose it, it will not work and you'll be very sad. Okay, moving on. So, multiplication. Let's rock and roll with that. Okay, so, those math skills, indeed. So, my chat is obviously, anyway. I'm going to try and not mention stream things while I'm recording this, because people on YouTube who watch this it's not live, it's going to be disastrous. So, we have the result, okay, which we'll just, we'll make a brand new matrix. Again, we're not using that diagonal because it won't be the same. I'm going to go through every single, basically I'm just going to make a nested loop here. It's actually going to be a triple nested loop. Right, but it will have, so this is going to go through all the rows, right, which is Y, all the columns, which is X, right, and then finally it's going to go through all of the actual elements, so I'll just call this E for elements, right, because it needs to add all of them together. So what it does is it has a sum, right, And then it says I'm going to add to the sum my elements, okay, at index x plus this element times 4, right? And to that, I'm going to multiply that. So this gives us, x is our column, right? I'm going to multiply our column by whatever the other lol. Let's get rid of this result. Other dot elements, because it's applying. We're not actually returning a brand new matrix. We're actually modifying our existing matrix. Okay. Other dot elements, and this will be just e plus lol. Don't ruin everything. E plus y times 4. Okay, that's our sum. And then all we want to do is set the appropriate. So this will get added up again the same way that I drew here, right? It's adding up all the appropriate rows and columns, right? And once it gets that sum and it finishes going through every row / column, it's going to go ahead and basically set our elements. We could probably hacks this. Actually, you know what? We'll set our elements at x plus y times 4 equal to that sum. Okay, that's all we're doing. And again, we're setting our elements. This is the elements from this class. Okay, and that's all we have to do. Again, we're not returning a new matrix in this situation. We're just modifying our current matrix to make it something else. Now, that's pretty much it. Okay, there's nothing too special about that. Let's move on to our next challenge, which is, you know what, let's just implement all these operators straight away. Okay, so I'm going to copy them. Whoops. I'm going to copy them. I'm going to paste them here, and we're going to deal with them. So that's done. And then, where are we, mat4? That's done. Okay, fantastic. So to deal with our good friend here, we'll be returning a brand new, I guess we'll just be returning a brand new one here. So all we really want to do for this is basically the same as this, but with having the result. So we'll have mat4 result, all right? We'll go ahead and we'll call, so left gets copied in. That's kind of the key here. So we'll go ahead and set that equal to left dot multiply right, okay? Left gets copied in, so this is a brand new thing, and really we just want to return that, okay? That's the idea, and we're returning a copy of it as well. So if this was a reference, remember, since this will modify our actual object, left would get modified, but without the reference, left does not get modified. Okay, here it's going to do the same thing. Again, this is a times equals, and it should be affecting our thing. So really all we'll be doing here is returning multiply other, and that is it. Okay, done. So those are those methods put away, and they should be absolutely robust and amazing. So orthographic and perspective matrices. Let's tackle these cats. Copy that, paste that, and let's begin. And make sure you don't forget the class namespace, of course, right over here. Okay, cool. So orthographic matrix. How are they constructed? What kind of magic is this? Well, luckily you all have access to the internet, I hope. Well, you are watching this video, so I assume you do. Orthographic matrix. How do we implement one of these? Well, it's simply like this, and that is a horribly sized image. Give me a bigger one. Okay, let's find a big one. This one's kind of good. It's a bit small, but... Okay, so we simply do this. So right, left, top, bottom, far, near. We've defined all of these things using this, right? So we can just implement that. In fact, that is slightly wrong. Give me a proper orthographic matrix. Here we go. This is what we want. Okay? This. So we've got near, far, top, bottom, and right, left. Okay? That's all we're doing. That is all we're implementing. And we'll do a similar thing for perspective. So if you're interested in where I'm getting all these numbers from, if I'm creating them, if I'm fabricating them, in my mind, the answer is no. I'm looking at one of these images literally, and I'm just copying it. Okay? That is That is the plan. So we'll be returning a new one, so we can return a new one. It'll be equal. We'll just use 1 here because again, if you didn't notice in my image, right, the last value is 1, so we're just going to initialize it to 1. To be lazy and not do that last value. And then what we'll do is fill out everything according to that image. So result.elements. Again, we'll use the indexing scheme. Again, this will be just 0, but it'll be more readable this way. 2 divided by right minus left. Make sure you get these in the right order, otherwise it'll be annoying. The next is just here. Right, we're going to set this to top minus bottom. This is honestly, like, orthographic is a pretty easy matrix to probably memorize as well. And this is simply going to be near minus phi. Again, make sure you get these in the right order. Getting them in the wrong order will matter since you're subtracting. Okay, I'm sure I don't need to mention that. So, and then finally, so this is those were the diagonal. Now we're doing the last column, right? So there's 3 of them, and then at the end we can just return result. So this is going to be, sorry, I should probably start this. So the row is going to be 0. The column is going to be the last one. It's always going to be the last one in this case. And then all we're doing is left plus right divided by left minus right. Okay, I'll copy this stuff because it's going to be kind of the same thing, except with the other planes or the other clipping planes. So we'll go bottom plus top and bottom minus top. And then finally, far plus near. And far minus near. Okay, and that's it. And then we'll return that result. And everything here looks pretty good to me. I'm happy with that, and we're done. Okay, that's the orthographic matrix. That's all we need to do. That's it. So, perspective. Let's move on to this. So again, if I bring up a perspective matrix real quick, and we take a look at it, it looks like this. So there's fun stuff involved, but it's relatively the same thing. So we clearly need tan. So to get tan, I'm going to have to include a math library of sorts. So I'm just going to include math.h. That's really all we need. So again, I'm going to do the same thing. I'm going to make a result. I'm going to, okay, so I'm going to set all these things up now. So we'll have, let's see, where was it? My image has disappeared. Okay, so we'll have a, okay, here's what we'll do. Okay, so result.elements 0 plus 0 times 4 will just be equal to, oh, this is going to be annoying. This is going to be a bit annoying. I'm just thinking of a smart way to do this. Okay, here's what we'll do. So we'll have float q equal to 1 divided by float. So, okay, so yeah, and then we'll do tan. Is there a 2 radians? Is there a 2 radians? Does the standard math thing have a 2 radians? I mean, we can make our own, but I don't want to do that. 2 radians C++. Is that a thing? Or do we have to make our own? Lol. Okay, is pi a thing? Maybe. Is this not a thing? Ugh. Okay, it is. It's m pi. And we have to define, use math defines. Okay, so m pi, is that a thing? Yes, it is. Okay, cool. So we've got that. Let's quickly make it 2 radians. I'll probably just put this in math, right? So we'll have a float to radians, float degrees, and then because I want to specify a field of view in degrees, and then all we'll do is we'll return degrees times, this is in radians, so degrees times m pi over 180. And we'll just kind of make that. Okay, that's all we need to do. Cool, so back in Mat4 land, we'll go tan, and then we have to, where's my image? Here's my image. 2 radians. Let's see. So tan returns a double, right? No, tan returns a float. Okay, well then that cast can go away. 0.5 times our field of view. So there we go. There's Q. A is going to be Q divided by aspect. So I'm kind of doing a few of these things here because we'll need them. And then over here I can set this equal to A because we'll need to set the next thing equal to Q, and then A, as you can see, was a product of Q divided by the aspect ratio, so I didn't want to recalculate things multiple times. Okay, so we got that. Okay, so this, let's see, B will be near plus far divided by near minus far. Okay, which is just yeah, which is just that one. Okay, so that goes in there, that goes into here. And then the next one, I think, where are we? The next one, okay, so there's -1 and then that. So we'll call this C. And that'll be 2 times near times far, near minus far. All right, cool. So, this will be, let's see, 3, yeah, 3, 2, and that'll be our -1. And then 2, 3. So last column, I'm doing this in column major, that's why I ordered it this way, it will just be C. Okay, and then that should be our projection matrix. Sorry, our perspective matrix. And in fact, that will conclude all of our, things. Okay, cool. So there we go. Let's go on to translation. So translation, is going to be, whoops. Translation is going to be very simple because as I think I mentioned this. Yeah, I mentioned this when I was talking about, oh, was I? No, I don't think I did. I mentioned this in the pre-show, but not the actual thing. So if you guys want to listen in on like the pre-show and whatnot, you have to make sure you watch the live streams. So translation matrix is really, really simple. It's simply an identity matrix, but the last column is the amount we want to translate by, and then 1, right? So it's just a normal identity matrix, and then we have this, which is just x, y, z. So when we take in a vec3, which is what we're doing here, right? We're taking in a vec3. All we want to do is we want to just have a, and we want to start off with an identity matrix, right? And then we simply want to set, again, the elements of that last column, right? Column 3, to be translation.x, translation.z, and translation.y. All right? And then we'll return the result. And that's it. So this is probably the easiest matrix of all. Okay? Scale is also very simple. So we'll do scale next, I think, and then we'll do rotation. Rotation's a big one. Okay? Okay. So scale is very similar to this, except instead of x, y, z being here, it's x, y, z, and then these are just 0. Okay. So scale is quite easy. In fact, here's a scale matrix for 2 dimensions, right? It's just like that. So this is the same thing, except we'll have as like a thing as well. So here we go, right? There we go. That's all we need. So for the scale matrix, I'm just going to copy and paste this. We're going to replace this with scale, of course. And then all these need to be replaced with 0, 0, 1, 1, and 2, 2. And that is it. Complete. So, rotation. I think that's the last one. Wow, good. I'm getting through this slowly. Let's see quickly. How are we for time? Goodish. I actually don't know how we are for time because it doesn't tell me. I don't know why I looked at that. Anyway, let's get back to this. So, rotation is going to be quite a tricky one because it's rather complicated. Let me see if I can find a good implementation of it. Here we go. So, rotation is going to work like this. We have an angle and we have an axis. If we want to rotate 45 degrees on like kind of in a 2D way, then we say we want the z-axis, and around the z-axis we want to rotate by 45 degrees. Okay. If we want to rotate by the x-axis, we pass in the x-axis. So how do we pass in an axis? We just, so obviously a vec3 contains x, y, z. We set the appropriate component of the vector to, let's just say 1. And if we have 1, 0, 0 in this vector, it will rotate around the x-axis only. Okay, and then we can obviously combine axes together if we wish. So we'll start off with an identity matrix. And then so first of all, I'm just going to convert our angle in degrees here to radians. Okay, next up, I'm going to calculate cosine and sine. So we'll call the cosine C. I'm going to calculate cosine and sine of our angle, or sorry, of our angle in radians. Okay, because I don't want to keep recalculating cosine and sine at the same angle multiple times when we need them, which is why I'm creating all these. Okay, and then we'll have... Okay, I'll just quickly bring this out. Again, a compiler will optimize this, don't worry. But I'll just bring out the x, y, and z axis into variables like this, just so the code will be a bit easier to read down below when we actually do the operation. That's probably all we'll need. So, oh, and then we'll go 1 minus c as well. We need that as well, so I'll call that OMC. Okay, so that'll be 1 minus c. All right, cool. So let's begin. So result.elements, the first one. Oh, and again, again, Google an image for this if you want to see what I'm copying from, essentially. It's just a simple... Ooh, I just lost us. Where are we? Here we go. Is this it? No. What? There we go, rotation. Oh, that was scary. Let's copy and paste this a bunch of times. So this is the first column. We'll set y times x times our wonderful omc variable plus z times our sine. And then I think this is the same, except it's a bit different in the sense that it's x times z instead, and it's minus y. So we just basically flipped around z and y there. Okay, cool. Next column is my personal favorite column. It's not actually. It's that minus z times s. I better not make a mistake here. Y times OMC plus c. Y times z times OMC plus x times our sine. Is this correct so far? Yes. Yes, it is. Good. And finally, 222 will be x, y, z. Okay, so the first one will be z plus y times s, y times z times c. The bad thing is we can't really verify that these are correct until we set up shaders. So we can verify stuff like multiplication, but we really can't verify this. So I really hope this is correct. That's it. So as you can see, it's pretty complicated. But let me quickly just go through this and make sure everything's correct before we move on. Yes. 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 Fantastic. So, that should be correct. Again, I don't know, and we'll find out once we actually launch it. But is that it? Once we actually get shaders and we can actually draw something, we'll make sure it's correct. And I really hope it is, because otherwise I'll have to amend this somehow. Anyway, there we go. So this looks pretty good to me. Let's test some of this out. I think that's it. So if we go back to main, let's create a matrix. So mat. So the simplest way we can check multiplication is by creating something like a translation matrix. So if I have, let's just say position equals, and let's, okay, so into the maths header, I'm going to add in mat4. Okay, cool. So in mat4, yeah, so for a position, we'll just set up a translation matrix, which will take in a vec3. So let me see. Let's just say 2, 3, 4, right? So, okay, we've got no way to print this, unfortunately. Okay, so we won't print it, we'll just look at it. So if we look at this, must return a value. Yep, whoops. Return this, okay? Don't forget to do that. Let's make sure we haven't forgotten to do that anywhere else. Nope. We haven't, good. So, yeah, let's run that again. 2 radians already defined in main. Oh, yeah, this is annoying. Where are we? So let's avoid this. It's because we've got, it's included in this as well. Here's what we'll do. We won't include maths here. We will define a, okay, oh, we want to have this in maths, obviously, by the way. I should have probably put this in here. But here's what we'll do. We'll have this out here. Everything's good in the hood. We'll grab this prototype, we'll pop it into the header in case we need it, and then, well, we will need it, and then over here I can just, in fact I don't even need to pop it in the header. I'll probably get rid of it in a minute, and then here we'll include a maths.h so that we get that. Okay, let's get rid of this. Alright, that's my master plan. 12 errors, lol, what just happened? What happened? Okay, let's also make it inline. What? What did I do? Did I do something bad? What did I do? I think I did something. I don't like this. No, it shouldn't be. It doesn't like me anymore. Yeah, I probably made it hate me. That's annoying. It is hating me quite a bit. Okay, let's see. I'm trying to quickly think of a useful solution to this problem. Okay. Okay, let's quickly grab the... Let's get rid of maths for a minute. That should fix our problem, apart from the 2 radians. And then what's all this? Okay, so we still needed that for maths. Okay, I see. Alright, let's do this. Okay. So we'll include... yeah, there's just not a great way to do this. Okay. We're going to make a new header file called maths func or something along those lines. We're going to go here and we'll pop it over here. Okay, this will be pragma once. It will include our sorry, it won't include any of our classes. It'll include math.h. And it will declare this thing. Where's my maths? Here's my maths. And then we'll just include maths func over here. And then we will we'll do this. We'll include that over here. Get rid of that. Okay, so now this will be all lovely. And then into mat4 we will include maths func. And then into maths we'll include everything. So this should work. What is going on? What is happening? Is it because of my fantastic method? Apparently not. This is just complete. Oh, it's because I don't have anything. Yeah, and then obviously we need to include into mat4, we need to include vec3. Is that it? Yes, there we go. Okay, good. So, double to float. Is this a double? Yeah, it looks like it. Okay, doesn't matter. That's totally fine. We can cast that to a double if we really want to. But we'll live with it. Okay, so that is it. So unfortunately that took longer than expected, but if we take a look at position right now, and in fact I'll just pop it into the watch so you guys can see it all right. These are our elements. So we should see 1, 1, 1, and then the last 3 should be, so that's correct, right? Now what I'm going to do is I'm going to take position and I'm going to multiply it with an identity matrix, such as that, right? And it should say the exact same. So if we relaunch this, I'll just stop it there. We'll make sure that okay, yep. We'll execute that, and then hopefully, yeah, okay, it looks exactly the same. So it looks like we probably worked. Yeah, I mean it's pretty there's no real way we can test this apart from manually actually testing it. The best way to test this is going to be once we get something onto the screen, we'll see if we can translate, rotate, scale different things together and see if those operations work, and then we'll know that, for example, multiplication was implemented correctly. But that's it. That's going to end this video. If you guys have any questions, post them in the comment section below. Next time, as per our plan, we will be looking at shaders, okay, and we'll move on to more OpenGL stuff, and we're pretty much done with maths for now, at least. So there we go. Those are our matrices. So we'll see them in action eventually. But if you guys enjoyed this video, please don't forget to hit that like button, and I'll see you guys next time. Goodbye.